Welcome back to Metaphor Math, and we're on to 2A. And in this problem, we're asked to prove something that might seem trivial to us, and it is trivial if you let it be. I mean, that is, you get out of a problem what you put into it. So, in in high school we might solve this problem, or elementary school we might seen this problem, and you might have solved it like where you just distribute the negative sign, and this becomes just negative a plus b, and then switch the order because the order of addition doesn't matter, and for the real numbers, so we just do b minus a, switching the order here, and we're done. We might say, okay, well, why in the world would they ask us to prove something that we've been able to prove years ago in our journey in mathematics? And I claim here that this problem is so valuable in learning how to be rigorous in proving statements, and not only be rigorous, but get the most out of problems. Because after all, we don't get anything out of a problem if we just give it a minimal kind of uh, superficial glance at it. So let's get the most out of this problem by leveraging the properties that are listed in the chapter, where they're the field properties, so the properties of a field and all of the consequences of these properties of a field. And we're going to prove this carefully and using rigor and practicing writing a careful, rigorous proof. So let's do that. So for problem 2a, they're asking us to prove that negative, parentheses a minus b, close parentheses, is equal to b minus a. And we might be kind of intimidated by this field, this term called field, and all these properties, commutativity, associativity, distributivity, and all of these other properties. But I encourage you not to be intimidated by them because they're simply things that we've seen before under the guise of a formal, or under the guise of formality, I should say. So don't be intimidated by this terminology and the formal language that they're using. So let's first start proving this, and let's try to be clever. Again, we're going to get out what we put into it. So let's try to be clever and prove this in kind of a non-intuitive way. And I'm going to do that by leveraging one of the properties listed in Intro to Analysis by Rosenlicht. And that property it's listed under F3, and it states the following. For any, this is the sign for any, upside down A, for any A and B and R, the equation A plus X is equal to B has one and only one and only one. Has one and only one solution. Now, let's try to see how we can use this to solve 2a. So I'm gonna say something here, and it might seem, kind of put it out of thin air, but it's gonna help us to see why this following proof is true. So let's say that a minus b, let a minus b equal to u. Now a minus b, since a is in the real numbers and b is in the real numbers, and the real numbers are what we call closed under addition and multiplication, meaning that the sum or difference of any two real numbers is also a real number, and the product of any two real numbers is also a real number. So a minus b is equal to u, and u is a real number. So now, the inverse of a minus b, the additive inverse, the number such that a minus b, the number such that when added to u, or which is a minus b, it equals 0. So the inverse of a minus b is negative u. Negative u is the inverse, the additive inverse, I should say, the additive inverse. And again, I'm leveraging one of these properties here, the additive and for any field, there exists an additive and multiplicative inverse for every element in that field. And R is a field. R is a field. I forgot to mention that's a very important fact. The real numbers are sometimes written in this blackboard bold notation, like this, and the real numbers are a field. So every element in the real numbers has an additive and a multiplicative inverse. Now, so negative u is the additive inverse. So negative u plus u is equal to 0. So now, let's state the following. A minus b plus x. Let me do this in a different color for variety. Let's do this blue color. A minus b, this element, a minus b, we could have said u here. A minus b plus x is equal to 0. And we know that this equation, by what I just stated, by F3 up here, and it's proven in the book, and it's not really proven in introductory analysis, but they claim that it's a rather trivial proof, and I encourage you to prove this on your own time, and think about why this is true. But this, by F3, has one and only one solution. And I'm going to say by F3. A minus b plus x equals 0 has one and only one solution. Now, since a minus b is equal to u, and negative u plus u is equal to 0, or another way of saying that by the commutative property, remember commutativity means that we can just change the order of the operation that we're doing on two elements. So this operation addition, we can just change the order of this operation. So negative u plus u is the same as u. This is the same as u plus negative u, and that's equal to 0. So a minus b, since this has one and only one solution, that is, the solution is unique, then this solution must be negative u. Negative u is equal to 0, because I said that u is equal to a minus b, so negative u must be the solution, since negative u plus u is equal to 0, and u is equal to a minus b, which is this element right here. This is u. So, but what is negative u? We can just substitute in a minus b. So a minus b plus negative a minus b is equal to 0. So a negative, so this implies, so negative a minus b is the unique solution to this equation. I'll just call it star. Let me do that star in a different color here. Let's do it in this orange color. Star 2, star. Now, I'm going to make a claim here. I claim that a minus b plus b minus a is also a solution to star. And remember, since star, this equation right here, must have a unique solution, it has to have one and only one solution, then if b minus a is also a solution, then that means b minus a must equal negative a minus b. And that means that we would be done. We would have just proved the statement. So let's try to do that. If we can show that b minus a must also be a solution to this equation, and since negative a minus b is the unique solution, then that means that b minus a must equal negative a minus b. If it didn't equal that, then this equation star would have two different solutions contradicting F3. So let's go about doing that. So a minus b plus b minus a is also a solution to star. Excuse me. I should have said the following. I should have said the following. I made a little typo here. A minus b plus. What I really meant to say is that b minus a is also a solution to star. That is to say, a minus b plus b minus a equals 0. Okay, so let's if that would be another way of saying that b minus a is a solution to star. So let's simplify this. Let's simplify a minus b plus b minus a. So let's simplify this expression here and see if we can arrive at 0, thus proving that b minus a is a solution to star. So I'm gonna kind of state what we're doing. This might be a way that you might write this out carefully if you were to ask. This is good practice for how to write out a proof like this carefully. So we show. I'm gonna write that up here. We show that a minus b plus b minus a is equal to 0. So now you might be saying again, well, I could just do all these manipulations that I've been doing since high school, and that'd be easy. This is easy. I've been doing this since I was in 7th grade. But let's remember, we're practicing our rigor and our carefulness in proving things. So let's do that. So a minus b plus b minus a. What is the definition? For the first thing I'm going to do is I'm going to remind us of the definition of subtraction. X minus y, if x minus y and x and y are real numbers, x comma y are real numbers. X minus y, the definition of this subtraction sign here is just shorthand for x plus the additive inverse of y. The additive inverse of y. So let's kind of leverage this definition of subtraction and rewrite this statement over here. This is equal to a plus negative b plus b plus negative a. And this is by definition of subtraction. Now, what can we do with this statement? You might be saying, well, the parentheses don't matter. And yes, that is true, but let's say that more carefully. We can leverage the associativity property. The associativity property of R. Since R is a field, then that means it must have the associativity property. So that means that these parentheses can be manipulated. So the grouping of these operations, which operations we perform first, doesn't matter. So let's do that. A plus, and I'm going to group it cleverly here, and you might be wondering, or you might know why I'm going to group this here, but it's obvious why I want to group it like this, because our goal is to get this statement right here to be equal to 0. So let's try to, we might be seeing already that this negative b and b will cancel out, but let's show that more carefully by leveraging the associativity property. Negative a. So now, we can group this like this. So this is by associativity, and since negative b is the additive inverse of b, then this means that that negative b plus b is equal to 0. So a plus 0 plus negative a. So this statement equals a plus 0 plus negative a. And this is by negative b being the additive inverse of b, because a field, when we add the additive inverses of elements together, when we add an element plus its additive inverse, when we add an element plus its additive inverse together, the sum of the element plus the additive inverse must equal the neutral element, or the additive identity, is sometimes what it's called. And the additive identity for the real numbers is 0. The multiplicative identity for the real numbers is 1. And what I mean by that is the additive identity plus any other element. So I'm going to say additive identity plus any other element a, in real, where a is an R, is equal to a. And same with the multiplicative identity. The multiplicative identity, ID, times a is equal to a. And again, this right here is 0, the additive identity, and this right here is 1, the multiplicative identity. This is just a quick reminder of what those terms mean, what I was saying. So back to our proof here. So a plus 0 plus negative a. Of course, this is a plus 0 is just a. And we could be even more rigorous. We could say, Well, this is the same as grouping a plus 0 plus negative a. And then this is by, let me mark this off right here. This is by associativity. And then a plus 0 is just a plus negative a. And this is by definition of additive identity. And then since 0 is the unique additive identity of the real numbers, and a plus negative a is, of course, 0 by definition of additive inverse. So, look at what we just did. I mean, it might seem trivial that we did this, but again, I encourage you to see that it's not. That we accomplished something rather nice by proving the statement in a non-intuitive way. We just proved 2a in a very non-intuitive way. We just showed that the equation a minus b plus x has a unique solution, negative a minus b, that is to say, the inverse of a minus b. And since this equation must have one and only one solution, and since we showed that b minus a is also a solution by all of our work here to the equation star, then we were able to show that b minus a must equal negative a minus b. So let's finish this out. This implies that negative a minus b is equal to b minus a, since star must have one and only one solution. That is to say, a unique solution.